Okay, recording is re-rolling on this Monday, November 1st. You guys just turned in an energy quiz, and we're starting on momentum. So you guys just watched a Magic School Bus clip where a pitcher threw the ball forward, she got kicked backward, and we're trying to figure out, I wonder if you could figure out her velocity moving backwards because she threw the ball forward. And that's going to involve this new topic, momentum and momentum conservation. So you guys picked up this half page that was clipped to the right side of your desk. You guys picked up your chapter 9 book problems, also clipped there. So your next assignment, or it's this set of problems from that chapter 9 page. Here's also a bonus assignment. Now, last couple of bonus assignments, I've been doing 20 points out of 10. I'm going to switch that to 20 out of 20 with this one going forward. But there's still some bonus points there. Bump up your grade a little bit to do that. And today we're going to go over a bunch of notes on momentum and momentum conservation. And well, I'll get probably about halfway through today, and then we'll pick up this story tomorrow. Right. So what is momentum? And how's it going to help us answer that baseball question? Now, the baseball question, we'll get closer to answering it by the end of today, but probably have to save that for first thing tomorrow. Okay. So momentum, I'm going to designate the lowercase p, lowercase level p, letter P. Why not M? Well, M is used for a bunch of other stuff you guys have seen in this class. Well, also I put, mass as a variable, like meter as a unit or milli as a prefix. So M is used all over the place. So we're going to use P. Also, I put a little vector arrow above that P. I haven't really been in a good habit of doing this a lot, but did I ever tell you guys what it stands for, or does anybody know if you put an arrow over a vector, over a variable, what that arrow means? It means it's a what kind of quantity?
Direct.
Yeah, a vector quantity, which means that direction does matter. Yeah, vector quantity. That's in contrast to a scalar quantity. The last couple of weeks we've been dealing with energy. And energy is a scalar value, so it has a magnitude, but no really direction that matters. Kind of like volume or mass. But now we're back to direction mattering. So what is momentum, say, as a formula? And then all it is, just very simply, is mass times velocity. Remember, these are vector values, though. Mass times velocity. What's a unit of momentum? Well, you can figure it out just from this formula. So, how massive is something? How fast is it moving? Well, how massive is measured in kilograms. And velocity, well, that's like meters per second. So there you go. That's it. Kilogram meter per second. Now, does that have a special name? Like I know kilogram meter per second squared is called a Newton. I know kilogram meter squared per second squared is called a joule. So does this have a name? As far as I know, it does not. So I'll just call this a unit of momentum, or kilogram meter per second. But it does have an alternate way of writing it, starting from newtons. Okay? So you guys can figure this out. You guys remember how Newton is kilogram meter per second squared? Right? Newton's second law of motion, F equals ma. Right? So kilogram meter per second squared. How do you get from this to this? It'd be newtons multiplied by what? To go from kilogram meter per second squared to just plain kilogram meter per second, you have to multiply by seconds. Yeah. So actually, either of these will work perfectly fine for a unit of momentum. This bottom one is more commonly used for like a change of momentum, called an impulse. I'll get to my notes tomorrow. If you apply a force for some time interval, that's how you change the momentum of something. Right? But we're not quite there yet. So give you guys this principle that's hugely important in this class, and that's that momentum is conserved in a closed system. Just like energy is conserved in a closed system. Okay, so there was conservation of energy. Now there's going to be conservation of momentum. Okay? So maybe I can say it like this. The sum of momentum initial is equal to sum of momentum final. Something like that, right? Okay. But you know what? There's actually a special case where you apply conservation of momentum. And that's for collisions. So good. Write some notes here, but make a note down here. Conservation of momentum is useful for solving collision problems. And I'll talk about why for the rest of classes. I'm going through some examples, like why would you specifically want to use this? Okay? So initial and final momentum is really pre-collision versus post-collision. So two things are colliding. Okay? Now, you guys have been through enough topics in physics now to see that sometimes there's multiple ways to solve things, multiple approaches that all lead to the same answer regardless. For example, a car braking to a stop. What is the stopping distance? Well, one approach could be you could do free body diagram, go through dynamics, and then to kinematics and solve for stopping distance that way. Another way you could do it, the way we did it last couple of weeks, you'd say energy is conserved and then solve it that way, or a little bit faster. Okay? But there's multiple ways to do it. But if you ever see anything colliding, like collisions, then, well, you do specifically want to use this method, because if you try to use other methods to solve collision problems, then you run into trouble. And as I go through some examples today, then that'll make more sense. Okay. You guys ready for next notes? What I'm going to do is refer to this page for a lot of the examples. Let's say like number 3. Okay, so let's take a look at number 3. Number 3 says two objects of measured masses collide head-on, resulting in these given measurements. What's the final velocity of object B after the collision? So I gave you mass of object A, mass of object B, their initial velocities before the collision, and then one of the rebound velocities. Can you solve for the other velocity? So this is for, let's do a general collision. Oh, also, I'm just keeping everything in one dimension today, so one dimension. So everything, oh, sorry, get back up here. All right, so in this case, maybe like right and left, something like that. So like a right-left axis. But things just moving forward and backward. That's it. Now, everything I teach you guys today, you can take into 2 and 3 dimensions, but let's not worry about that for now. Just focus on the fundamentals here. So I'm going to have some mass A and some mass B. And maybe they're headed toward each other at some VA initial and some VB initial. Right? And then these things are going to collide. Like, pow, there's going to be some collision. Okay? And then what? Well, think about it. There's actually a lot of things that could happen from the collision, maybe depending on the material properties of these things. Like maybe they collide and stick, or maybe they rebound off each other really well. In fact, if they rebound off each other really well, do you think that might look kind of like this? Like really bouncy? So how they bounce off each other, maybe that has something to do with the answer to this problem. So let's do redraw mass A right here. It could possibly rebound though, so maybe I'll draw it doing that. We'll call this VA final. Okay. And then maybe mass B also has like a rebound kind of motion. So VB, or sorry, mass B, okay. Move its own VB final. Now this is all really in terms of variables, just very generic. Let's tag some numbers to these things. I'll call mass A 3 kilograms, mass B 2 kilograms. So 3 kg and 2 kg. Okay. I need to give you their initial velocities. So and you have to know how fast they're going towards each other. Let's call this guy 10 meters per second. And this guy I'll call negative 15 meters per second. Right? So 15 to the left. Okay. Now there is a little more stuff I have to tell you, but I'm going to pause right there. And here, let's just go like we're solving the thing. So the sum of momentum before the collision is equal to the sum of momentum after the collision. Got that? Right. And now you guys know the sigma means sum of, like we're adding up a bunch of little parts. Right? And so we just got 2 objects, so it's going to be 2 parts. Right? Momentum is mass times velocity. Mass A, velocity A initial, plus mass B, velocity B initial. Okay? And then after the collision, mass A, velocity A final, plus mass B, velocity v final. Okay, got it right? Okay, so then we go start plugging stuff in. So I got 3 kilograms moving at 10 meters per second, plus 2 kilograms moving at negative 15 meters per second, because opposite direction, right? Staying in one dimension though. All right, that's going to be, see, 3 kilograms moving at some, actually, leave the blank right there. Pretend that you didn't write that V. Okay. That's just blank. Right, plus 2 kilograms moving at however fast that's moving, right? Is that right? Okay. Now here's where maybe intuitively you sort of figured this out before I wrote anything, or maybe you're looking at this now saying, I see 2 unknowns. See, we don't know velocity A final. We also don't know velocity B final. Right? We don't know either of these rebound velocities. If that's true, can you solve 2 unknowns with just one equation? No, there would be lots of possibilities. But this is where I want to tie this algebra back to the physics that it actually represents. Right? Which is that we can have different kinds of collisions going on. Right? You might have something like this. This is called elastic, by the way. Elastic just means it's really bouncy. It means that kinetic energy specifically is conserved in the system. I'll give you guys some examples as we're going on so we can see some numbers. Okay? But this might be in contrast to, like, what if these balls were made out of wet clay? These ones just like stuck together. We'll also solve that later today. But this might be just some generic situation where maybe maybe these are like half-deflated tennis balls, so they like rebound off each other, but not very well. So it's like, bam, it just like slowly bounce away from each other. So I have to give you one more number. I'm going to tell you VA final. I'm going to tell you this rebound velocity. Let's say it's negative 6 meters per second. Right? So it rebounds at 6 to the left. Right? Now I can plug that in here. Call this negative 6 meters per second. Right? Now I can solve for VV final. Right? Because once I tell you one of the rebound velocities, now it is like set in stone determinable exactly what the other rebound velocity had to be because of this principle right here. Momentum is conserved. Okay. All right, well, let's add up all these momentum bits. Right. It looks like object A had 30 units of momentum. Object B had negative 30. 30 plus negative 30. Hey, what's that? 0 momentum? Wait, is that true? Was there really 0 momentum in the system to start out with? Yeah, on net there was 0 kilogram meter per second. Right? Positive 30 plus negative 30 does 0 out. Now, that's not universally true. I just made up the numbers to do that. But remember, we're dealing with vector values. So that would also be true over here. This better total to 0 units of momentum. Now, this bit right here, I see negative 18 kilogram meter per second. And then plus 2 kilograms times VB final. Okay. So add 18 units of momentum over, divide by 2. VB final is equal to 18 kilogram meter per second, all divided by 2 kilograms. That gives you 9 meters per second. Okay. So now we figured this out. So that's equal to 9 meters per second. Yeah, that's how we know. But if I gave you a different rebound velocity, then this number would be different, right? Like that rebound velocity is negative 6 meters per second. Like I just made that up, right? Hey, could I make that anything? That negative 6 meters per second? Like, could I make it negative 1,000,000? Could these bounce off each other and like rebound, and this would be like negative 1,000,000 meters per second? That seems wrong, right? So maybe this number could be a lot of things, but it's probably bounded by something, right? By some physical condition. And so that's what I want to talk about now is let's go to energy accounting because we spent the last couple of weeks looking at energy. Let's look at, yeah. 9 meters per second. Okay. Let's do some energy accounting on this. Say what is the initial versus final kinetic energy? So kinetic energy, let's say like pre-collision. That was your 1/2 mv initial squared. Well, for each bit, right? So 1/2 mv squared for each bit. Okay. And Here, I'll just do this on my calculator screen. So take a look at this initial setup. So 1/2 times 3 kilograms times 10 meters per second squared. So that many joules plus 1/2 times 2 kilograms times, now negative 15 being squared, doesn't the negative just go away? Is that whatever? Okay. I'm looking at 375 joules. 375 joules of kinetic energy going around in the system. Okay. Versus, what is the kinetic energy post-collision? Well, do the same thing right here. So 1/2 times m times 6 squared plus 1/2 times this m times this 9 squared. Looking at 135 joules? Huh? 135 joules. Okay. So the final kinetic energy is actually less than the initial kinetic energy. Okay. Looks like we're missing, what is 375 minus 135? We're missing 240 joules. So 240 joules went somewhere. Went where? Because we spent last couple of weeks of class talking about how energy is conserved. And now what, all of a sudden just 240 joules just going to disappear? Well, it doesn't disappear from the universe. It just changes from mechanical energy to non-mechanical forms. So it goes into so you can say it went into non-mechanical forms of energy. I'm talking about things like heat, sound, permanent deformation. So if you hear like bang, where that sound energy come from? Or if you measure the temperature, that the temperature would go up a little bit. Or permanent deformation could be like if you fire a bullet into a block of wood. Do you think a lot of force times distance went into like pressing the wood fibers out of the way? Probably something like that. Right? Okay. Now maybe. Hopefully you guys are seeing like why you would not want to use conservation of energy for collisions, right? Because there's going to be like missing mechanical energy. Now, the energy doesn't disappear; it just goes into forms that we have trouble accounting for in this class. Right. So during non-elastic collisions, some mechanical energy is converted into other forms. So we're talking about heat, sound, permanent deformation. Fire a bullet into a block of wood, has to permanently deform that wood and press the fibers out of the way. A lot of energy goes there. Okay. Now, notice I said non-elastic collision, okay? Because there is one exception to this, and that would be an elastic collision. Okay? So elastic collision just means something super bouncy. Here's the closest example I have in this room. Okay? Is something like doing that. Probably like as bouncy as you can get. Okay? And the physics interpretation of that is that, well, not only is momentum conserved, which is like a law of the universe, but also that very special kind of energy called kinetic energy also happens to be conserved. So if the post-collision kinetic energy happens to be equal to the pre-collision kinetic energy, you're looking at something that's perfectly elastic. It's like perfectly bouncy. Okay. Now, this is a side note that I'm gonna just plant right here right now, but tomorrow we'll look at the result of the system of equations between kinetic energy and also momentum being conserved at the same time. One more thing I'm going to do before I switch this page off. I'm going to go back up to this inequality right here. See what it says the post-collision kinetic energy is less than the pre-collision kinetic energy, right? We lost these 240 joules. I want to modify this. Instead of saying strictly less than, let's do this. Let's say less than or equal to, because you could have something that's elastic. If something's perfectly elastic, like perfectly bouncy, in that case, it would be conserved. You guys had bouncy balls a week ago. You guys remember those bouncy balls? Right? do you think those bounce balls would probably be pretty close to this model, like perfectly elastic? Right? If it was truly perfectly elastic, then you could bounce it off the floor and just go bounce, 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 bounce. You could do that for like thousands of years. Right? Just bounce, 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 without losing anything. All right, so let's look at number 4 on this hot sheet. Number 4. Okay. Now, number 4 is actually it's not too different from what we just did. I'll even use the same numbers as we just did. Okay. But there's one little change, and the little change is that instead of giving you a bunch of initial, like pre-collision information, I give you a bunch of post-collision information and ask you, like, can you solve for what happened before? Okay. So I'll use the same numbers just so that you can say, like, oh yeah, that did work out, like exactly the same way. Compare your notes. So number 4, okay, I'll go through this kind of fast. Okay. There's a point that I want to make with this though, so let's run the numbers first and then. So mass A, 3 kg, mass B, 2 kg. They're headed towards each other. VA naught. Now this one I'll give you, I'll call it 10 meters per second, just like before. Well, let's say that we don't know what VB naught is. Solve for that. But you do know this. After they slam against each other and rebound, yeah, well, VA final is negative 6 meters per second. So now that's going to be a given value. And VB final called 9 meters per second. That's also a given value. Okay. So let's do momentum accounting. Sum of momentum before collision is equal to sum of momentum after collision. Okay. MAVA naught plus MBVB naught is equal to MAVA final plus MBVB final. Right, like that. And let's plug in some numbers. I mean, at this point, it's just kind of a plug and chug situation because you know how this works. You know, this is going to be 3 kilograms shows up there and there. Plugging stuff in. 2 kilograms shows up here and here. Plug that in. I told you this number is 10 meters per second. Okay, so it looks like, okay, going 30 kilogram meter per second, just like in the last setup. Except this time we're solving for what was BB in the initial situation. Okay. Now, after they collide, mass A rebounds at 6 meters per second in the negative direction, and object B rebounds at positive 9 meters per second. Okay. Guys, what is the momentum in the system after the collision? So what is negative 18 plus positive 18? That is 0. I mean, obviously it's got to be because using the same example numbers as before. Okay? So if you go solve for VB naught, right? Subtract 30 units over. So 10 times 3, subtract that over. That'd be negative 30. Divide by 2. Wouldn't VB naught have to be negative 15 meters per second? Okay? Which was the given value in number 3 in the notes, right? So yeah, it's just the same thing but backwards. Right? So what's the point of all this? The point of this is that because you can go backwards and forwards with conservation momentum, you could apply exactly this type thinking at number 4 to, let's say you were a forensic investigator and you saw a car crash. You're trying to figure out like what were the speeds of these cars before the crash. Right? You might be doing something pretty similar to like exactly this. Because if it's a crash, okay, that's a collision. Conservation of energy, that's not really going to help you. A lot of energy went into like probably crumpling the cars. Right? But you can do conservation of momentum and get a real accurate picture of maybe like how fast were the cars going before they collided. Like, if you do the speed of one car, you can figure out the speed of the other. Like, say if you're looking at the tire tracks on the road, skid marks, something like that. Okay. All right, let's go to look at situation number 5. Number 5, even at a glance, you can tell the table looks different. Right? So how's this one different? 2 objects collide and stick together in a perfectly inelastic collision. Right? So perfectly inelastic, that means they collide and stick together. Right? But think of this way. This is sort of like a boundary condition on collisions. Right? This could be one extreme thing that could happen. could be they collide and stick. The other extreme, of course, would be perfectly elastic, and that's like Newton's cradle. But we're not going to get to this until tomorrow. Right. So collide and stick together, perfectly inelastic. Right. Given the masses and initial velocities of the objects, what is the final velocity of the two objects after they stuck together? Right. Well, let's chase this down. Right, so, zoom out. Perfectly inelastic collision. That just means they're going to collide and stick. Now, if they collide and stick together, hey, doesn't that mean they have the same final velocity? Right? Which is a good tidbit to know because something I wanted to point out on this page is notice that number 3, number 4, which very similar to each other. I gave you 5 values you solve for the 6th one, right? So 1, 2, 3, 4, 5, you solve for the one unknown. Okay. But in number 5, the one we're doing now where they collide and stick, notice I only give you 4 pieces of information. Now I remember a few minutes ago, we started off with 4 pieces of information and that was not solvable. Right? So if you only have 4 pieces of information, that's not enough to solve a collision situation. So your 5th piece of information that actually makes it solvable is the fact that they do stick together. So they must have the same final velocity. Let's get a picture for this and then jump into the equations and see how this is going to play out. So let's go, I'll even use the same masses and starting velocities as before. Let's have mass A be 3 kg, mass B be 2 kg, just like before. Let's have VA naught be 10 meters per second, and VB naught be 15 meters per second, but it's negative, right? Because it's going backwards. Negative 15 meters per second. Okay. Now, so far that looks like it's starting out the same. But what if these are not half-deflated tennis balls? What if these are like balls of clay and it's like just stick together? I wonder what's going to happen as a result of that collision. Well, let's do momentum accounting. Sum of momentum before collision is equal to sum of momentum after collision. Okay. So this will start out just like before, mass A, velocity A initial, plus mass B, velocity B initial. Okay, so far it looks the same, right? Equals. Okay. Now I could finish this off with just the general equation, MAVAF plus MBVBF, but if VAF and VBF are the same, you can just factor that out. So let's just jump to the next step, or you might even just start from thinking about this, that they would be effectively like one giant mass moving at some common final velocity, right? Doesn't that have to be the case for perfectly inelastic? Let's plug some numbers in, see what happens. So we got 3 kg moving at 10 meters per second, plus 2 kg moving at negative 15 meters per second. And that's going to combine to make 3 plus 2 kg. Move in, well, how fast? Okay. Now, since it's the same numbers that I had before, you guys might remember sort of where this is going. What is 30 units of momentum minus 30 units of momentum? Just 0 units of momentum. Not universally true, just true for this problem. Okay. So how fast is 5 kilogram blob of clay going to be moving? I see it's just going to be 0. It comes to a dead stop, right? Okay. So we got a big mass moving slowly to the right and a small mass moving fast to the left. It's like just come to a dead stop for the numbers I did. Okay. Is that okay? Another note about this, though, is let's look at energy accounting. So what's the kinetic energy before and the kinetic energy after the collision? Okay. Now, we've already calculated the kinetic energy before. We did it right here. We did it on a calculator screen. 1/2 mv squared, sum it up for both parts. It came out to 375 joules of kinetic energy. 1/2 mv squared with this masses and initial speeds. Okay. But afterwards, hey, if the final speed is 0, and you run 1/2 mv squared for a 5 kilogram blob, then how many joules of kinetic energy? Also 0, right? Ooh, that looks like a bigger change in kinetic energy than the half deflated tennis balls. Half deflated tennis balls, there was a change of 240 joules of kinetic energy. Okay. Here, it's all 375 joules of kinetic energy. And then keep in the back of your mind, when we eventually get to elastic, like perfectly bouncy, like Newton's cradle, there would be no change. It would just, like, all 375 joules would be conserved. Okay? Who's got a question so far? This all good? All right. Because next thing we're doing here is, well, let's take this and put it in reverse. Let's go to number 6 on this half page. Okay. Number 6 says, a grenade flying through the air. At some given velocity explodes into 2 parts that travel along the same direction that the grenade was originally traveling. Hold on a minute. I thought conservation of momentum had everything to do with collisions, and here we've got an explosion. What's this about? How's this tied to conservation of momentum? At what velocity is piece B of the grenade traveling? Hint: apply perfectly inelastic collision formula in reverse. I gave you the 2 masses of the fragments of the grenade. I told you how fast the grenade was originally thrown and how fast one of the pieces is going after the explosion. And what does that have to do with a perfectly inelastic collision? Of course, I'm going to tell you guys, but you can figure it out before I tell you. So let's get a picture going and make sense of this thing. Okay. So this is number 6 on that half page. We got this big old grenade, and it's moving at some initial velocity. Let's say V naught is 15 meters per second. I'm just going to use the number straight off the page. Okay? And this is going to break into 2 parts when it explodes. There's going to be some mass B and some mass A. Okay? And mass B was like 0.6 kilograms, and mass A was like 0.4 kilograms. This thing is flying through the air. Just for simplification a little bit, let's just keep it along one axis of motion. Okay. Now you guys know really it's following like a projectile parabola type path, but this say it's going approximately forward. Okay. So it's gonna, after it explodes, break into mass B and mass A. They're gonna go off and do their own separate things. Okay. Now, how exactly are both fragments going to fly off after the explosion? Well, probably depends on how big that explosion was. Right? So, yeah, I have to write a little bit more, but some space there. We'll start doing momentum accounting and then go back and fill in the details that we need. So, see if you guys can figure out what you're missing. What else do you have to know? So, sum of momentum before the explosion equals sum of momentum after the explosion. Well, momentum before the explosion, wouldn't that be just like the giant mass moving at that grown velocity? Right? So that would be ma plus mv, just as one solid mass moving at some initial velocity. Right? That one mass, by the way, is 1 kilogram. You guys you see 1 kilogram, right? Okay, let's take this right here. So here's your grenade. Take this, check this. Okay. It's going to explode into 2 parts. So each part is going to have it's a momentum that they have to collectively add up to the original momentum. So mass A, velocity A post-explosion, plus mass B times velocity B post-explosion. Just like that. Now I did give you some numbers, so let's start plugging in those numbers to this formula to make an equation. And that is that this is collectively 1 kilogram, because 0.6 plus 0.4 kilograms. Okay? Moving at 15 meters per second. That's going to split into, well, mass A was 0.4 kilograms, BAF plus 0.6 kilograms on mass B, moving at dBF. Okay, now we're running into the situation we did before where there's one equation with 2 unknowns. So, okay, so you do need more information. Here's where I'm going to go back and fill in those details. Okay. I got to tell you, one of the post-collision velocities. It could be either piece. I'll give it to you for piece A. Now, piece A, I'll have it going faster than the thrown speed. So VA final is, let's call it 20 meters per second. I don't think this is at all realistic for a grenade, but let's just use the numbers, right? Now, piece B, I mean, if this was really realistic, it'd probably be like blown backwards. But at least it better be slower than 15, because one piece takes off faster than 15, and momentum is conserved. The other piece got to be going slower than 15, right? Or faster in the opposite direction. And the way this one's going to work out is just going to be slower than 15. So I'll call this VB final, and we're solving for that. So let's call this 20 meters per second. Call this VB final. Okay. So, okay. Now, one thing we could do, we're about to do anyway, is just plug and chug and get the answer. But before we do that, I want you guys to see like why this is a conservation of momentum problem, why it's perfectly inelastic in reverse. You guys see that if you had a grenade that was flying through the air and explodes into two parts, and you run that film in reverse, let's say you film this thing and run the film in rewind, it's like, wouldn't that look like a collision of two pieces, like perfectly inelastic collision? That's exactly what it would look like, wouldn't it? That's why conservation of momentum would work out this way. But there's another part to the story, which is that energy conservation, or, well, looks like it's not conserved. Remember how two objects collide and stick? It looks like there's a huge kinetic energy loss. Now, of course, that energy just goes into deformation sort of thing, right? But if you just run this film in reverse, do you think there would actually be more kinetic energy post-explosion than pre-explosion? In fact, that does make sense, doesn't it? Because I bet there's a lot of energy associated with that explosion. There's a lot of energy in those chemical bonds that made the thing explode in the first place. Yeah, so we would be getting lots and lots of extra energy out of this thing. Right? So that would be a terrible way to answer this, but let's do momentum accounting. So I got 15 units of momentum. And it's going to go 8 units are going to route into that piece, and the other 7 are going to route into piece B. Right? So velocity B final is equal to 15 minus 8, that's 7 kilogram meter per second, acting on 0.6 kilograms. I got BB final is 11.7 meters per second. Okay. And notice it is slower than the original throwing speed, which of course it would have to be. And if I made realistic numbers, it really should be like negative, right? But what is this good for? What kind of problem could this solve? Well, suppose you knew how fast you threw a grenade and you knew the energy associated with that explosion, and you're hunting for the grenade fragments. And you find one grenade fragment, and you, okay, I found like right over here. If you know enough physics and the conservation of momentum, you could get a pretty good idea of where the other piece landed by doing exactly that right there. You say, oh, well, it must be like somewhere there. All right. Any questions from today so far? All right. So yeah, that's about all the time I got in class today. But tomorrow we'll look at remember that baseball problem? That baseball problem? That's going to lead directly from this, because that pitcher throwing the baseball is like her plus the baseball, just one giant mass sitting on the mound at rest. Right? And then she throws the baseball, and the baseball's going to have some speed forward, and she and her mass is going to have some velocity backward. Yep, you guys see how that's going to be momentum accounting? So we'll answer that question, which is just this basically. Right? And then we'll look at perfectly elastic situations, which is, again, that's just Newton's cradle right here. This is like perfectly bouncy. That's the other extreme you could have. From perfectly inelastic, this is perfectly elastic. Okay. We'll look at coefficient of restitution. That's the way you can measure bounciness, like how bouncy something. And then we'll look at impulse, which is the change in momentum, which you get from a force applied for a time interval. So that'll be tomorrow's adventure. And of course, I got labs lined up for you guys and do some textbook problems with you guys.